Hi, in this class we are studying definite integrals of type 5. Integral of the form integral minus infinity to infinity r of x into e raised to ix dx, where the degree of denominator of r of z is only one unit higher than that of the numerator, and r of z has a real pole, that is, the pole lies on the real axis. The integral does not converge if r of z has a real pole. However, the real part or imaginary part of the integral can converge if the real pole of r of z cancels with a 0 of sin x or cos x, and if the pole is a simple pole. Method of integration. We may assume that the only real pole of r of z is a simple pole at the origin. Choose gamma as the perimeter of the rectangle with the vertices x2 plus iy, minus x1 plus iy, and minus x1, where the origin is avoided by a small semicircle of radius delta in the lower half plane, this circle. When x1, x2 and y tends to infinity, the integral over the upper horizontal side and the two vertical sides tends to 0. Let C be the semicircle of radius delta in the lower half plane, this semicircle, and its equation is z equal to delta e raised to I theta, where theta ranges from pi to 2 pi. Let capital B be the residue of r of z into e raised to iz at z equal to 0. Then r of z into e raised to iz equal to b by z plus r naught of z, because b is the residue, it is the coefficient of 1 by z. Therefore, at the origin z equal to 0, the residue is b, therefore this term can be written as b by z, which is the coefficient of 1 by z. Therefore, r of z into e raised to iz can be written as b by z plus r naught of z, where r naught of z is analytic. Now, equation of the semicircle C is z equal to delta e raised to I theta, where pi less than or equal to theta less than or equal to 2 pi. Then integral over C r of z into e raised to I z dz, this integral of this, equal to integral over C b by z plus r naught of z dz, which is equal to integral over C b by z dz plus integral over C r naught of z dz, which is equal to integral theta ranges from pi to 2 pi. So we can write integral from pi to 2 pi. B by z is delta e raised to I theta and dz is delta e raised to I theta into I d theta. Therefore, delta e raised to I theta is cancelled. Therefore, this can be written as integral pi to 2 pi b by delta e raised to I theta into I delta e raised to I theta d theta plus integral over C r naught of z dz, which is equal to, if this is cancelled, we get I b into integral pi to 2 pi d theta plus integral over C r naught of z dz, and this integral is pi. Therefore, this is b pi I plus integral over C r naught of z dz. Now, this can be written as b pi I plus 0, because integral over C r naught of z dz tends to 0 as delta tends to 0. So, it is b pi I. This tends to 0 because we know that r naught of z is analytic in a neighborhood of the origin, and r naught of z is bounded in that neighborhood. Therefore, modulus r naught of z is less than or equal to m. Therefore, by m into L inequality you have studied earlier in B.Sc classes. We have modulus of integral over C r naught of z dz is less than or equal to. If we replace this by m, then we get m into integral over c dz, which is L. So this is less than or equal to ml, where L is the length of C. Therefore, modulus of integral over C r naught of z dz is less than or equal to m into length of C is pi delta. The complete circle is 2 pi delta. Therefore, semicircle is pi delta. Therefore, m pi delta is here. Then when delta tends to 0, this m pi delta tends to 0. Therefore, integral over C r naught of z dz tends to 0. So this part tends to 0. Therefore, b pi I is this. Therefore, integral over C r of z into e raised to I z dz is b pi I. Now, when x1, x2 and y tends to infinity and delta tends to 0, integral over gamma r of z into e raised to I z dz is integral along this part, from this part and along these three parts. Integrals over these three parts are 0. Therefore, integral over gamma r of z into e raised to I z dz is integral from here to here. So this is integral minus infinity to minus delta r of x into e raised to ix dx. We use x because on the real axis z is denoted as x, plus integral over c r of z into e raised to iz dz, plus integral from delta to infinity r of x into e raised to ix dx. Taking limits on both sides, and as delta tends to 0, this is this itself, integral over gamma r of z into e raised to iz dz itself, which is equal to limit delta tends to 0, integral minus infinity to minus delta r of x into e raised to ix dx, plus this integral is b pi I from this part. This integral is b pi I, plus limit delta tends to 0, integral from delta to infinity r of x into e raised to ix dx, which is denoted as 1. Now by residue theorem, integral over gamma r of z into e raised to iz dz equal to 2 pi I into sigma y greater than 0 residue of r of z into e raised to iz plus residue of r of z into e raised to iz at z equal to 0, which is equal to 2 pi I into sigma residue of r of z into e raised to iz when for y greater than 0, plus this residue is b. If we remove the brackets, we get integral over gamma r of z into e raised to iz dz equal to 2 pi I into sigma y greater than 0 residue of r of z into e raised to iz plus b into 2 pi I, which is denoted as 2. From 1 and 2, the left hand sides are same. Therefore, the right hand sides are also same. So if we get these two, we can cancel b pi I from this side, from this. If we write this in the left hand side and this on the right hand side, b pi I is cancelled and this becomes 2 b pi I minus b pi I, which is b pi I. So from 1 and 2, we get limit delta tends to 0, integral minus infinity to minus delta r of x into e raised to ix plus limit delta tends to 0, delta integral from delta to infinity r of x into e raised to ix dx equal to 2 pi I into sigma residue of r of z into e raised to iz over y greater than 0 plus b pi I. This limit on the left hand side is called Cauchy's principal value of integral minus infinity to infinity r of x into e raised to ix dx. This is called Cauchy's principal value of integral minus infinity to infinity r of x into e raised to ix dx, and is denoted by like this: principal value of integral minus infinity to infinity r of x into e raised to ix dx, or p of integral minus infinity to infinity r of x into e raised to ix dx. And this integral will not converge. Therefore, we can write this as principal value of integral minus infinity to infinity r of x into e raised to ix dx equal to 2 pi I into sigma over y greater than 0 residue of r of z into e raised to iz plus b pi I. We can write like this. Since if the real pole cancels with 0 of sin x or cos x, then the real part of or imaginary part of this integral, if we find this integral, then the real part or imaginary part of the above integral converges. That is, the real part is integral minus infinity to infinity r of x into cos x dx, or the imaginary part is integral minus infinity to infinity r of x into sin x dx converges, or these integrals exist. Note that the above result can be generalized even if there are finite number of simple real poles. Then principal value of integral minus infinity to infinity r of x into e raised to ix dx equal to 2 pi I into sigma or y greater than 0 residue of r of z into e raised to iz plus b pi I, which is equal to 2 pi I into sigma over y greater than 0 residue of r of z into e raised to iz plus this b is residue of r of z into e raised to iz at y equal to 0 into pi I. Thank you.